Our third and final speaker for today's webinar is Karen Stone. Karen is the Program Manager in the Bureau of Safety and Environmental Enforcement's Oil Spill Preparedness Division. Karen was trained as a petroleum engineer and earth scientist. The bulk of her 3-decade career has focused on emergency and oil spill preparedness. Karen's current focus is on in-situ burning as an oil spill response tool. Part of Karen's fun times during COVID, while she's been locked down in Northern Virginia, has been allowing her time to start some knitting projects and to dust off her guitar to get some practice in on some of those rusty chords. So we're glad that Karen was able to join us today, and feel free to start sharing your screen.
So yes, I am with the Bureau of Safety Environment Enforcement, which is a mouthful, so we call it BSEE. BSEE is part of the Department of the Interior, and we were stood up as an agency after the Deepwater Horizon disaster. And I have a lot of technologies that I wanted to share with you today about in-situ burning, but I'm just going to hold it at about 5 different technologies. I think you'll find them very exciting. I partner a lot with other federal agencies. There are about 15 federal agencies that are tasked with oil spill response and emergency preparedness. So I partner with groups like EPA with Brian Gillette, NOAA, PHMSA, my sister agency, BOEM. So we do a lot of partnering, and it really ensures that we have a good, robust program. So the first thing I'm going to talk to you about is in-situ burning, which is the focus of today's meeting. And for those of you who don't know, in-situ means in place. So we're actually burning the oil in place. And in this case, we're burning it on the water. And the benefits of in-situ are many, and really the benefits outweigh any negative problems that might be associated with the tool. So first of all, it reduces the amount of oil on the water and on the shoreline. So that really helps protect sensitive habitats where we might have different types of marine animals and birds and other type of wildlife. It greatly reduces the storage that would be needed for any oil collected, transporting that oil and then disposing of it once we get it to shore. It also eliminates air quality issues. Believe it or not, the burning of the oil quickly gets rid of some of those more volatile components. So it helps protect the worker safety out there, the first responders, but also onshore populations. And then finally, this particular method is a lot less labor intensive than some of our other methods. So I need you to put on your high school caps and go back to your high school chemistry class and just a real quick review of in-situ burning. So on the left side of the equation, we have hydrocarbons, okay, which is crude oil. And we want to burn those. And the products we get on the other side of the equation are water vapor, water vapor, carbon monoxide, okay, that makes up about 85% of what we have. And then the remainder is particulate matter and some of the other gases. And the gases tend to dissipate fairly quickly. But in-situ burning, okay, it's an ideal tool because it can remove anywhere from 90 to 98% of the oil that is spilled on the water. The first thing that folks notice when they see in-situ burning is this horrible black plume that we see. Okay, there's my cursor. And we get this plume because pool fires, in-situ burn fires, are starved for oxygen. These fires can be anywhere from 800 to 1,000 feet across, okay? They're absolutely huge, and so we can't get oxygen into the center of them. And unlike the diagram that I showed you, the graph in the slide before, okay, the hydrocarbons are not completely destroyed. So not only do we have the black plume, we have residual oil, which is unburned oil or thermally, damaged oil. Okay, and in this area of the plume, we actually do get some elevated particulate matter, which can impact first responders. But again, that tends to dissipate fairly quickly. On your screen right here are some pictures, or is a picture of some of the burns from the Deepwater tragedy. And during this course of the summer, from April 28th to July 19th, thereabouts, there were over 400 successful in-situ burns, which removed 310,000 barrels of oil off the surface of the water. So what I aim to do with my research is I'm looking for new techniques and technologies to increase these burn efficiencies. So even though it's already efficient, over 90% efficient, we're still trying to improve this method to get rid of that black plume and to try to eliminate more of that burn residue. How do we determine if the technique or the technology is working? We use measurement. We use science to look at the data and to compare the different techniques and technologies to see if we are making improvements. So some of these emissions sampling techniques, they've really evolved over time. The first one in the upper left-hand corner is actually down in Mobile, Alabama, by Missy, where she is. And there's a little sand spit in the middle of Mobile Bay, and it's a U.S. Coast Guard Naval Research Laboratory facility. And there's a burn pan there. And this picture was from 1995, when some of the aerostats were up and doing the emissions measurements from there. Fast forward 20 years to the next picture down here and also the one on the right, and we did some more burn tests down at Little Sand Island, and we have got Coast Guard personnel, and they've got some of their smart monitoring equipment here on some buckets. And then also we have a windsock that has the sensors miniaturized, so we have them there. And then with Brian's equipment with the EPA, we have some of the full-size sensors, and then his Calibri that he was just talking about, where the sensors are miniaturized and he has them up on drones. So BSEE has teamed with the EPA to quantify emissions and the burn residue and to determine how efficiently these fires burn. Okay, so we've been working together with the EPA for about 3 years now. And in addition to the EPA conducting some of the measurements for me, when I have my various researchers working, one of their requirements is always that they measure the emissions so that we can share or show and demonstrate that indeed the technique or the technology is reducing the emissions. So the first project I want to talk to you about is a system, an insulation system. The ocean is a tremendous heat sink, and when we burn oil on water, we have to get the oil hot enough so that it'll release the vapors to burn. The oil itself is actually not burning, it's the vapors above there. And so we get that burning, and this system was hoping to insulate the oil from that cold water below. So we were not able to use drones at the time and Brian's unmanned vehicle. So we had to dangle his equipment on an aluminum skid and have it dangling from a crane. And the crane was really agile and was able to keep his sensors in the plume. And the measurements found out that unfortunately, this system did not work, but that's the nature of R&D. And I put this in there intentionally because not all research does work, but we know this because we have the data, we have the science to show that the burn efficiencies were not satisfactory. So the next project that I have, it actually was successful. And this was looking at different boom geometries to try to increase the efficiency. So a couple of slides before, I told you that these burns are absolutely huge. They're about 800 feet across, and the interior of them is just starved for oxygen. So we were looking at ways that we could change the geometry of the boom to allow more oxygen to the center to make them more efficient. So these boom systems that you see here and in some of the pictures from earlier today, one single system costs about $350,000, and each system is only good for about a half dozen burns. So by looking at different geometries, we might be able to make the equipment last longer, but also get rid of that plume and help reduce the amount of burn residue we have. So in the upper right-hand picture, we have more of a typical boom configuration that we studied. The next one on the upper left is one that is a little bit more narrow and long. And then the final, the bottom one, very long and narrow that we could try to get a lot of oxygen in there. And then the bottom right, you can see Brian's equipment. And I did not put a red circle there, but with my cursor, that is the emission sampling equipment. So Brian was able to show that, yes, indeed, that really long, narrow configuration achieved what we want to. We have higher burn efficiencies, we have lower particulate matter. All right, so another project that we're working on is a fire whirl. And I'm gonna escape out of here, I hope, and get over to YouTube. And you know what, it's not gonna go, and we are not going to have the gods of the technology, we're not going to make them unhappy, I hope. So we're just going to go to the full screen of this, but it's a fire whirl. And this fire whirl, again, this is a phenomenon that we saw down at the Deepwater Horizon. And if you look at this picture, you can see that instead of the black plume, the plume is a little bit lighter gray. This tells us that perhaps there's less soot, but there was no science, there was no data on this fire whirl phenomena. So we reached out to the University of Maryland, where they have some combustion engineers and scientists at their program, and we asked them to study fire whirls. So this video you see on the left is actually a pool fire, a pan fire of crude oil. The stem you see in the middle of the fire, that is the thermocouples that are measuring the temperature. And this fire is about 0.7 meters, which is just a little bit over 2 feet. And the fire is reaching about 8 feet. This next video is a fire whirl that we were able to form. It's the same burn pan, so it's 0.7 meters in diameter. Once this fire whirl gets going, you can't tell it from this picture, but it actually reached 18 feet high, which is the level of where we have a fume hood above it to capture the emissions for measurements. So we were very excited about the results of this. Again, there was no science or literature on fire whirls to remediate hydrocarbon spills, but what we found was that they did indeed reduce the amount of emissions that we had. We had increased burn efficiency, and I'm looking at my notes here. So fire whirls burn twice the volume of oil in half the amount of time, reduce the emissions, and reduce the burn residues. So we were very excited with this technology, and we're in the process of awarding a follow-on study for that one. All right, the next technology I wanted to share with you is a flame refluxer system, which is again a mouthful, but that's the technology that we're working with scientists from the Worcester Polytechnic Institute, WPI. For fires, about 95% of the energy from any fire is actually lost to the atmosphere. So what this technology does is it has these heat collectors that reach up into the flames, and this is copper, so it conducts that heat back to a copper blanket that floats on the oil slick so that it heats up the vapor, or heats up the oil to release the vapors, because again, it's not the oil that's burning, it's the vapors that are hovering above the oil slick. So we were very excited about this project as well. So one way to measure fire efficiency is by looking at the ratio of carbon monoxide to carbon dioxide. And we saw a great increase in the efficiency of the fire. But what we were really excited about was also the burn residue. And I'm going back to this picture. One of the reasons I was excited about this project is I thought that this copper blanket could capture and collect any of the burn residue from the burns. But what happened is that the fires burned so hot and so efficiently, they acted like a self-cleaning oven, and there was no residue to capture. And the final piece of equipment that I'd like you to share with you today is our BSEE Burner. So this burner is designed for emulsified crude oil. When crude oil spills on water, it quickly changes. The wind and the wave action whip the seawater into the oil, and it creates this big emulsion. It's like very thick, and actually oil spill response workers refer to it as chocolate mousse. This mousse is very difficult to ignite. If there's too much water in it, really anything over 20–25%, you can't ignite it at all. So BSEE partnered with the Naval Research Laboratory to design this burner. And what this burner does, it atomizes the oil, the emulsions, by combining it with air. And it atomized the oil into very small droplets, making them available for combustion. And what I want you to notice in this picture on the right is that, yes, I have some high level clouds up there, but there's not that big sooty plume that is associated with in-situ burning. So this video, there we go. That's just a really quick capture of the emulsifier or the burner working. And what we found is that the carbon monoxide was almost undetectable. Soot emissions were very, very low. And Brian and his team at the EPA, they determined that the average of the test, a 99.9% burn efficiency. So this is absolutely amazing. So we're hoping this burner can work for not only emulsions, but for population centers or for very remote locations such as off of Alaska, or even around the world where we have some of these World War II wrecks from ships that went down and ships and they're now leaking. So we can capture the oil and collect it and then burn it off and not have to store and transport it. So that's just a couple of the projects that I wanted to share today. And I have all of the reports in a lot greater depth on the BSEE website. So here's that information where you can find the reports. And if you want to get in touch with me, here is my email as well, karen.stone@bsee.gov. So thank you very much.